So we're ready to make the following claims. The eigenvectors fall along two separate lines that divide the plane into four regions of distinct behavior. These are referred to as the straight line solutions. So you could have an initial condition that falls along that straight line, and if it does, it'll just propel at a linear pace outwards. That doesn't mean that the graphs of x versus time and y versus time will be linear, because that depends on the size of the vectors, and those are changing, either shrinking or in this case getting longer and longer. The eigenvalues tell us which way the vectors point along those straight lines. So that's the green arrows I have drawn here. If lambda is bigger than 0, vectors point away from the origin, the only equilibrium point. If lambda is less than 0, vectors point towards the equilibrium point, the origin, which is the only equilibrium point. And then eigenvalues and eigenvectors stated together help us determine where a solution will flow to within any one of the four subdivided regions of the plane. So I didn't have to show you any of these vectors. All you needed was just the two eigenvector lines and the corresponding arrows here, and you could have sketched without seeing any of these red arrows inside of that plane. So we'll go ahead and take a look at an example now. Oh, and then why does this make sense that solutions are going to flow like this? Well, let's think about what happens in the long run to each of these terms in our general solution. So here, as t approaches infinity, this term right here decays to 0. So this will go to 0 as t approaches infinity. So that's kind of why we can think about the solutions here as coming in a little bit. We have decay in both of our x of t and y of t, because notice they both contain that e to the negative 2t term that will eventually approach 0. It just kind of depends on which of these four regions you start in. So the solution gets closer to 0, 0, but then as t gets larger and larger, these guys deviate off to either plus or minus infinity. It depends on the value of k1, whether that coefficient ends up being positive or negative, and this goes to plus or minus infinity. That helps us see that eventually, once that t becomes big enough, and depending on the size of the positive eigenvalue, the bigger it is, the faster it'll kind of curve back out. So now you can see that both x and y are going, in this case, to positive infinity. And here you can see that both of the solutions that start off here are going to eventually deviate to negative infinity. And same here, deviate to negative infinity in both directions. And here they'll both increase to positive infinity. So it's just the values of k1 and k2 that will determine whether these terms are going to have positive or negative coefficients. So with that said, let's consider another example so we can see how this will work. Consider the completely decoupled system, dx dt equals 2x and dy dt equals 1y. Find its eigenvalues and eigenvectors and sketch the plane along with straight line solutions. Then sketch its sample trajectory for an initial condition within each of the four regions, i.e. let's do something like this just by using the eigenvalues and eigenvectors. Verify with the Grapher app. Note, we already know the system has solutions x of t equals k1 e to the 2t, because guess what? This is completely decoupled, and if something grows at a rate proportional to itself, then it's going to be an exponential function with that constant of proportionality. Same thing for y of t, that's just going to be k2 e to the 1t. So let's just set this up to get it into matrix form. So we have dx dt equals 2x. Again, list that x term first. It has 0y in it. And dy dt equals, 0x plus 1y. And so that tells us that our A matrix is the matrix 2, 0, 0, 1. So this, even though this is a completely decoupled system, this approach allows us to solve a linear system regardless of whether it's completely coupled all the way down to completely decoupled. So it's a really fast approach to solving these equations. And so, lo and behold, we get our lambda and we get our v1, v2. So that means that the y, the solution vector, is going to be k1 e to the 2t v1, and v1, we should note, is the vector 1, 0, plus k2 e to the 1t times v2, which is 0, 1. And notice that when this distributes, the k1 e to the 2t will just end up in the x position. So we'll have 1 k1 e to the 2t, and then y, and then this will have k2 e to the 1t times 0. So we're not going to write any other terms there. Here we'll have k1 e to the 2t times 0 for y of t, k2 e to the 1t times 1 for y of t, and so we end up with exactly what we thought we were going to get. So that's very, very nice, a very, very handy approach to being able to solve these. Now we wanted to sketch the phase plane, so we're going to do that next, and all we really have to do is mark down or plot the lines on which our eigenvectors lie. So let me kind of label this 1, 2, 3. We'll go 1, 2, 3 in the other direction. 1, 2, 3. 1, 2, 3. So the eigenvector 1, 0, that has a 1x component. So a run of 1, a rise of 0, and that tells me that this vector is going to fall along the x-axis. So here's the vector 1, 0 right there. The vector 0, 1 is the vector that lies along the y-axis because x is 0, y is 1. So that's going to be, whoops, a couple of extra things on there that I didn't want. So we'll draw this vector as starting there and pointing straight up. So that means what I can do here is I can think about this axis as being the straight line solution for V2, and I'll do in green, right, because we said that the entire line that this eigenvector lies on is going to be that straight line solution. So that's going to be all the way across right over here. Now, and that's for 1, 0. Now the eigenvalue is positive 2 on the 1, 0 vector, so that means that these guys, these arrows on that straight line are going to point straight outwards this way. So let me take away these two vectors real quick so that we don't get confused about the arrows we're drawing on them. And same thing goes for over here. On this side of the equilibrium point, those trajectories are going to flow outwards. Same thing here. They're going to flow away from the origin because I have an eigenvalue of positive 1, and away from the origin down here because I have it's the same eigenvalue. So here's my equilibrium point, and we see that all solutions, what they're going to do over time is if we imagine that these dictate where the solution goes, these are just going to go outwards and away from the origin. Now they could be kind of curved. We don't really know that based upon just this simple drawing, but we just want to kind of sketch that these solutions are going to go away from the origin. So it depends on where your initial condition is, but you're always going to go to the infinities in both directions. And we can justify that because if we look at k1 e to the 2t, as t becomes infinitely large, this thing either approaches positive infinity or negative infinity, and that ultimately depends on whether k1 is positive or negative for our specific initial condition. Same thing here. As t approaches infinity, k2 e to the t will approach one of the infinities, again, barring the sign of k2. So if we want to take a look at the actual phase plane, we should see the same thing. So here we have it. You can see I have dx dt equals 2 times x, dy dt equals 1 times y, and in the phase plane, I see, again, those distinct vectors that point straight outwards from the origin right along the x-axis. And same thing over here. The y vectors, it's a little bit harder to tell, but these vectors point straight up, and you can see that the vectors surrounding it have upward components to their vector tips. And same thing down here, these point straight down. And now you can see that although we didn't get the curvature right, you can see that if we start off with an initial condition here, x approaches negative infinity over time. That's this graph here. And again, it looks exponential because our solution is exponential. And y of t, y is growing. The y component of these ordered pairs along my cursor are getting bigger and bigger away from the origin, and so y is approaching positive infinity. Over here, similar type of thing, except here both of them are going to infinity. Down here, same thing, but here x is going towards positive infinity. That's this graph. Y is decreasing towards negative infinity, so there's that graph. And then similar type of behavior over here, x to negative infinity and y to negative infinity as well. So pretty cool stuff. And again, just remember you can change your Tmax if you want this to only show the trajectory for, say, 1 second. It'll still show the entire trajectory here, but it'll only show you 1 second of the graph. So in 1 second, you can kind of see what happens to x, which is this picture, and y, which is this picture over here. And here I just put that into our document for reference purposes so that we can see that our picture and the actual picture look very similar. So this demonstrates the real power of working with eigenvalues and eigenvectors. These are really complex looking systems, but they have these beautiful features that really help us understand what's going on in the long run.